Okay, so let's take a look at an example of something that has a double bond. Okay. So here we have a sigma bond, sigma, sigma. But this double bond is 1 sigma and 1 pi. Okay, so carbon, we looked at carbon already, right? So carbon we know will make 4 hybrid orbitals with 1 electron in it each, right? We've already talked about this. Now, what we haven't talked about yet is what happens if we have a double or triple bond. Now, normally carbon, you would say, okay, carbon is sp3 hybridized since we've already discussed this. But when you have an element that normally hybridizes but is involved in multiple bonds, you only hybridize for the number of sigma bonds that are required. Okay, so what I mean by that is this carbon, let's look at this one in more detail, this bolded one. This carbon needs 1, 2, 3 sigma bonds. The other bond is going to be a pi bond. Okay, so this is important because pi bonds cannot happen with hybrid orbitals. So what that means is, of these 4 electrons, only 3 out of the 4 are going to be hybridized. And the reason for that is because we need a regular p orbital left over for a sigma. So instead of hybridizing all 4, we're actually only going to hybridize 3. So if you recall, sp2 is when we need, I even wrote sp3. sp2 is when we need 3 hybridized orbitals, similar to when we looked at the boron example. Now this electron that's left over is going to be a regular 2p, an unhybridized electron in that orbital. So the carbon on the opposite side is exactly the same. It also needs 1, 2, 3 sigma and 1 pi. So I'm going to do the second carbon in a different color just so we can see that. So it's also going to have sp2, 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 and a 2p. And I'll do them in opposite. So when you're doing the bonds where we're going to draw the rectangles, you have to remember that the hybrids are only for these sigma bonds. So for example, carbon and carbon needs to have 1 sigma and 1 pi. So that means when I'm going to bond these 2 carbons together, I need these regular 2p's to be my pi bond. Right? This is my pi bond, my side-by-side interaction. So the hybridized ones that are overlapping is going to be my sigma. So notice there's 2 rectangles that are happening between the 2 carbons. This is my double bond, a sigma and a pi. This is my double bond right here. So you're probably wondering, well, what's going to happen to these other ones? Remember, we have other atoms that we need to add in. So this carbon on the left here needs 2 hydrogens. So there's 2 available for that. Let's make my hydrogens red. A 1s. Right? So here's my hydrogen bond. So let's say this one here. And I have to do the exact same thing to another hydrogen. So here are my 2 hydrogen bonds and my double bond between the carbons. The last 2 that are left over are for the 2 hydrogens on the other end. Don't forget that you need to label everything, and you also need to make sure that the spins are opposite spins. So here is my last hydrogen. So the carbon on the left has 2 hydrogens and then a double bond. And then the carbon on the right has the double bond with the carbon as well as 2 hydrogens. So you only really have the hybrid orbitals for the number of sigma bonds that are required. So here is that actual exact same thing that we were looking at. So notice this is the carbon. So instead of hybridizing all 4, only 3 out of the 4 are going to be hybridized. So the sigma bonds are all here. So look at this carbon here. So we have sigma, sigma, sigma. So this is carbon, carbon, hydrogen, hydrogen. The side-by-side interaction is what this is showing here. This is our pi bond. Okay, so pi bonds is where you have not an overlap directly, but a side-by-side interaction. Okay, now let's take a look at what happens when we have a triple bond. Okay, so we have sigma, sigma. If you recall, I mentioned that a triple bond is sigma plus 2 pi bonds. So what does that mean for our carbon? So carbon still has 4 valence electrons that are going to spread out. But let's look at this one on the left. The number of sigma bonds we need is 2. So we're not going to hybridize all 4 here. We're going to hybridize 2 out of the 4. So instead of being sp3, it's actually going to be sp because we're only hybridizing 2 orbitals. The other orbitals are going to be regular p orbitals because we need those regular ones in order to create those pi bonds. Remember, you cannot make a pi bond with a hybrid orbital. So there's one carbon. The other carbon is exactly the same. It needs 2 sigma bonds and 2 pi bonds. Oop, oh my goodness, I need to do them upside down. So they're opposite spin. So we have sp, sp, 2p, 2p. So notice there is a triple bond, 2 pi's. So here is 1 pi. Remember, you're doing the regular 2 p's. Here is a second pi, and the sigma has to be made with the hybrid orbitals. So notice there are 3 rectangles going between the 2 carbons. It's because we have our triple bond there. So again, what are these other hybrids there for? They're for the hydrogen atoms. So each carbon has a 1s hydrogen that it is bonding to. So one on this side and one on the other side. Okay, now what this looks like is that you're going to have sigma bonds. So here is this is the exact same example. It's ethene. This is the same example from before. So it's just another picture of it. This is the double bonds again. We've already looked at this in depth. So this is the triple bond example. So here you have, this starts to get really messy if you haven't noticed. So we have here the sigma bonds between the hydrogen, the carbon, and the other hydrogen and carbon. So notice they're trying to point at this here. These are sigma bonds. And the pi bonds are the interactions between the regular p orbitals. Now, when you're drawing these, I will not expect you to draw a triple bond with the 3D diagrams, okay? You can do it in this way. So I will expect you to draw a triple bond using orbital diagrams and Lewis structures, but I will not ask you to draw a triple bond using the 3D representations. It just becomes just way too unclear because you start having these pi bond blobs that make it difficult to see what's happening, okay? Now for a double bond, yes, you can be expected to draw it because really you have all your sigmas and there's going to be only one side-by-side interaction. It becomes more difficult if you have more than one of those side-by-side interactions. Okay, so this is just another, just showing you all of the sigma bonds. So here are the SPs and the 1s overlaps. And then here are the pi bond overlaps where you have basically what the 3D representation would be this and this combined. So these are all the sigmas Plus you would have your pi bonds drawn in here as well. So it's a little bit messy. So we would, for the triple bond, we're going to stick to just the orbital diagrams. Okay, so again, this is just to recap. We've already covered all of this. Any single covalent bond or the first covalent bond in a double triple bond is a sigma bond. If you have additional bonds, so the second bond or the second and third in the triple bond, they are pi bonds. Okay, so we've already looked at that. Now, the last piece here is discussing really the strength of these bonds. So pi bonds are actually much shorter than, it makes the molecule a much shorter molecule in comparison to ones that only have single bonds. However, even though the molecule becomes shorter, you would think that this would become more difficult to break in a chemical reaction. But actually, it's untrue. Pi bonds are much easier to break apart than the sigma bond, the original single bond, is. So when we get into our next unit, where we're going to start looking at chemical reactions involving molecules like this, you're going to notice that molecules that have double and triple bonds are much more reactive than molecules that have only a single sigma bond. And the reason for that is because the side-by-side interaction between p orbitals is actually much weaker than when you have the direct overlap. So the end-to-end overlap is a much stronger bond. It takes more energy to break this than it would to break that side-by-side interaction. Okay, for this last step, I'd like you to pause the video and try drawing a carbon dioxide molecule. So start with the Lewis structure. Then I'd like you to do an orbital diagram. Okay, orbital diagram. And then lastly, I want you to try doing a 3D representation for it. Okay, so give it a try. So these first two, you shouldn't really have too much of an issue. The last one might be a little bit more complex, but I'm going to work it through with you. So pause the video, give it a try. Okay, so for the Lewis structure, that should be pretty straightforward at this point. So you should have a double bond between carbon and each of its two oxygens. Now, that means we have a sigma and a pi on both sides of this. So carbon, instead of having all four of them hybridized, look at the number of sigmas that are required. It needs one for either side. So that means this should be sp hybridized and have two regular 2p's. So oxygen, really what you're going to do is you're going to have one oxygen, right, on one side. Each oxygen needs, so I kind of messed up my order here, but that's okay. So we're going to have one bond that's going to be a sigma bond with the hybrid orbital. And we're going to have one bond that is going to be the side-by-side interaction, right? So we have a sigma and a pi. The other oxygen is going to do the same thing, but with the remaining orbitals. So you have sp with a 2p for the sigma, and then this is going to be really weird, but instead of drawing a regular rectangle, that's okay. As long as if I can see which ones you mean that are doing the overlap, that's fine. We have a 2p pi bond. Okay, now for the 3D representation, we have carbon with sp and sp on either end. So remember, oxygen has two 2p's. So here is oxygen. The sp2p overlap is our sigma. So we're going to do the same thing on the other side. I haven't drawn in, oops. So this is a 2p and another 2p. So here are my oxygens and my sigma bonds. Now carbon has two regular peanuts that are here, a 2p and a 2p. One is doing a side-by-side interaction on one oxygen, the other on the other side. Okay, so you don't have to draw them super close. just show a line connecting where the pi bond is existing.